This video deals with work and energy. Now in physics, work is defined as the product of force times displacement times cosine theta, where theta is the angle between the force and the displacement. The units are something called joules, and a joule is defined as a kilogram meter squared per second squared. You might remember that in Newton, the units of force here, was a kilogram meter per second squared. We multiply that by the units of displacement, which are meters, and so we get that. Simple example here, we want to find the work needed to pull a box in the direction shown, that's this direction here, for a displacement of 2 meters if a force of 15 newtons is applied along this rope here. Notice that this angle here is 30 degrees. So to compute the work, we're going to take 15 newtons times the displacement, 2 meters, times cosine of 30, and we get 26 joules. A couple of things to note here. First of all, if the force and the displacement are in the same direction, so like if the displacement was this direction and the force was this direction, then the equation reduces down to work is equal to force times distance, and that's because this angle here would be 0 degrees, and the cosine of 0 is 1. Also, notice that if there is no motion, if you're applying a force, but there's no motion, no work is done. And of course, that's because the displacement here would be 0, and that would mean the work is 0. Okay, so here are a couple of illustrations that will help you get a better understanding of work. Here's a man that's mowing the lawn. Notice that the force is down in this direction, but the displacement, the mower is moving in that direction. So when you compute the force, you would have to use this angle between the force and the displacement. In this case over here, the displacement is 0, so like we said before, the net force is going to be 0. In this case, the work done is also 0, and that's because the force is being applied upward, but the displacement is perpendicular to it, and the cosine of 90 degrees is 0. So therefore, the work done is 0. So that's true always. If the force is perpendicular to the displacement, then the net work done is 0. In this case, the briefcase is being brought up the stairs, so the displacement is in that direction, but the force to support the weight of the briefcase is upward in that direction, so we would need to use this angle in here to compute the work. And then finally, in this last example, the force on the briefcase is upward because, again, we have to support the weight, but the briefcase is being lowered, so the displacement is in that direction. So that means that the angle here between the force and the displacement is 180 degrees. The cosine of 180 degrees is -1, so therefore this is negative work, and that's because the briefcase is being lowered rather than raised. Another way to look at this is that the briefcase is doing work on this electrical generator. Okay, so the next thing is the work-energy theorem, and we're actually going to derive this because it's actually pretty easy. So the way that we're going to do this is we're going to substitute Newton's second law equation into the work formula. Okay, so we're going to be assuming here that the force and the displacement are in the same direction, so work is equal to force times displacement. F equals ma, we're going to substitute that in for the F, so that gives us work is equal to mass times acceleration times displacement. So now we're going to take one of our kinematics formulas, you might remember this one, we're going to solve it for the acceleration, so we get that expression, and then we're going to substitute it in right there for A, so that gives us work is equal to mass times Vf squared minus V0 squared divided by 2d times d. Notice that the displacement here cancels out, and then we're going to multiply each one of these terms by 1/2, which is the same as dividing them by 2, and then multiply through by the mass. So in other words, this gives us work is equal to 1/2 mv final squared minus 1/2 mv initial squared. Now this term, 1/2 mv squared here, is defined as kinetic energy, which is energy of motion. So this tells us then that the work done on an object is equal to the object's change in kinetic energy. So if you're applying a force in the same direction as the displacement, then that means that the kinetic energy is going to increase, right? Because you're going to be applying a force and it's going to accelerate, and that's going to mean the velocity gets bigger. So the kinetic energy is going to increase. By the same token, if the object is moving to the right here and the force is applied to the left, then the work done is going to be equal to the decrease in kinetic energy. The kinetic energy is going to get smaller. So, in essence, then, if you do, for example, 100 joules of work on an object, the kinetic energy of the object is going to change by 100 joules. It may increase or it may decrease depending upon the direction of the force. So here is an example. We're going to apply a constant force of 120 newtons to a 30 kilogram package through a distance of 0.8 meters. We're assuming that there is friction, so the force of friction is 5 newtons. Now the package is going to start from rest, so we want to find out the increase in kinetic energy of the package and then also the resulting velocity. Okay, so we're going to use the work energy theorem. So work is equal to 1/2 mv final squared minus 1/2 mv initial squared. But the package starts from rest, so this initial kinetic energy here is going to be 0. So therefore, the increase in kinetic energy is going to be the net force on the object times the displacement. Okay, so now notice this is the net force. So we're applying a force of 120 newtons, but there is an opposing force due to friction, which opposes the motion of 5 newtons. So the net force is 115 newtons, and the displacement is 0.8 meters. And again, we're assuming that the force and the displacement are the same direction, so that gives us 92 joules as the increase in kinetic energy. Now we can compute the velocity of the object because we know that the kinetic energy is 1/2 mv squared. So we can take this, now we know the kinetic energy, we can solve for the velocity, so that gives us the square root of twice the kinetic energy divided by the mass, so 2 times 92 joules divided by 30 kilograms, and that's going to give us 2.48 meters per second. Now, notice that the units do come out correctly because if you recall from the previous or one of the previous slides, that a joule is a kilogram meters squared over a second squared. So the kilograms will cancel, so then you'd be left with meters squared over a second squared, and when you take the square root of those units, of course you'll get meters per second. Okay, so now we're going to talk about another kind of energy, potential energy. And we're going to start off with gravitational potential energy. So let's look at an example here. If you had a 2 kilogram book on the floor and you wanted to lift it up to a table which was 4 meters high, then the work done, which is force times distance, the force would be, you'd have to apply, is equal to the weight of the book, mg, and the distance would be the height of the table. So 2 kilograms times 9.8 meters per second squared, the acceleration due to gravity, times the height of the table, 4 meters, and that would be 78 joules. Now, we say that the book has gained 78 joules of potential energy, energy of position. And potential energy is computed by the formula PE equals mgh. So the work done obviously is equal to the potential energy gained. We use the same formula to compute both. Now, potential energy is often converted into kinetic energy. So, for example, if you have this book on the table and you push it off, the book falls down. Now, as it falls to the floor, it loses potential energy, but work is being done on it by gravity, and that increases its kinetic energy, because as it falls, it's going to be going faster and faster, and it's going to it's going to gain kinetic energy. So ultimately then, the amount of kinetic energy it gains is going to be exactly the same as the amount of potential energy that it loses. Okay, so here we have an example of a roller coaster right here, and we want to find out the velocity of the roller coaster at the finish line here. First of all, A, if the roller coaster starts from rest, or B, if the initial speed of the roller coaster is 5 meters per second. In both of these cases, we're assuming that friction is negligible. Okay, so however much potential energy that the roller coaster loses, however, whatever that number is, that's going to be equal to the kinetic energy gained by the roller coaster. So if we just look at the path here, we can see that it starts here from rest. It's going to go down this incline. It's going to gain kinetic energy down on the bottom here, and it's going to lose potential. But then, as it goes back up again, it's going to gain back some of the potential energy, and it's going to have kinetic energy right here. But ultimately then, the amount of kinetic energy that it has here is going to be equal to the amount of potential energy that it loses, which is going to be as a result of this height difference. Okay, so what we're going to do is we're going to set the mgh, the amount of potential energy it loses, to the amount of kinetic energy it gained, in this case 1/2 mv squared. And we're going to solve for the velocity. Now notice that the masses here are going to cancel, so v is equal to the square root of 2gh, so it's going to be 2 times 9.8 times 20 meters, because that's going to be the height difference. And so ultimately then, the roller coaster has a speed of 19.8 meters per second. Okay, now in the second case, it has some kinetic energy to begin with. So therefore, we can say that the potential energy that it has up here, plus the kinetic energy that it has, is going to be equal to the final kinetic energy. So in other words, whatever potential energy it loses is going to have to be added into the amount of kinetic energy that it has here at the beginning. Okay, so we're going to say potential here, mgh plus 1/2 mv squared is equal to 1/2 mv final squared. So the final velocity, solving for v here, the final velocity is going to be equal to the square root of 2gh plus the initial velocity squared, which is equal to square root of 2 times 9.8 times 20 meters times this initial velocity of 5 meters per second squared, and we solve and it comes out to be 20.4 meters per second. Notice that the velocity here at the finish is going to be a little bit bigger than it was up here. And of course the reason why that is because it started out with some kinetic energy here, so it had more energy to begin with than it did in the first case.